All right, Marty, do you want to start? Great. Okay, well, welcome everyone. On behalf of ARMA and the Technical Committee on Induced Seismicity, we welcome you to our monthly webinar series. So the committee chaired by Ahmad Gassami, myself co-chair Sean Maxwell, and then along with Jens Lundstern and Marty Haddad, the committee, we welcome you to our webinars. So if we move to the next slide, today we're honored to have Mariana Rodriguez with ExxonMobil speaking. So Mariana's been doing some very interesting work looking at data-driven risking assessment for induced seismicity. So obviously a topic of interest to the community and a great piece of work. I've seen bits from some industry meetings, and then I believe some of the material was presented at ERTEC this summer. So a bit of an encore performance for Mariana. So we thank her for her participation and look forward to her webinar. Before we get started, just a few announcements. So I'm going to pass it over to Jens.
Okay, and I'm just going to skip the usual slide that shows the upcoming presentations scheduled for future months. We are working on those right now, and there's actually been a change since we announced the next speaker last time, but expect to get emails if you're on the distribution list and so on for the upcoming webinars, most likely the first Friday of each month as usual. And I'd also like to raise attention for, there's a call for abstracts for the ARMA Symposium. It's the 59th U.S. Rock Mechanics and Geomechanics Symposium happening in Santa Fe, New Mexico in June 2025. And note the very soon imminent abstract deadline of 16th of October coming up here. You can go to Santa Fe 2025.armarocks.org to learn more about that.
Good morning, everyone. This is Mahdi Haddad from the Bureau of Economic Geology. Thanks again for joining us for another great webinar. This is our 53rd webinar of our Induced Seismicity series of ARMA. Before starting the webinar, I would like to highlight some logistical points. First, feel free to share the webinar invite with your colleagues in order to pass the message to interested people to the topic of induced seismicity. Please share their contact information if they would like to be added to the webinar invite list. And please submit your questions during or after this talk in the chat button at the bottom of the Zoom meeting window. And please send these questions to all of the to everyone in order for us to organize the questions and use better of time at the end of the presentation. And this meeting is being recorded, and after approval by the presenter, we can share it in our YouTube channel. And also the recordings are available on our Induced Seismicity Technical Committee YouTube channel. And basically the link to this YouTube channel is in the invitation email. Please subscribe to this channel to receive notifications about these recordings. And also please stay muted during the talk. And we would like to have no distraction to the presenter during the talk. But we will have this opportunity for everyone during the informal section of the webinar to get unmuted and ask verbal questions. Without further delay, let's invite Mariana to take over the stage. Mariana?
Okay. I'm sharing my screen. Let me know when you see it.
Yeah, we can see it, Mariana. You're good.
Okay, cool. Let me move this towards here. Okay. Okay. Well, good morning. Thank you for being here today. As I was introduced, my name is Mariana Rodriguez. I work in ExxonMobil. And today I will present some of our work on data-driven risking for induced seismicity. This work was performed with two of my colleagues from ExxonMobil, who are Yang Cheng and Stefan, who's another. Stefan is in the call today, and he will be also sharing some materials towards the end of the presentation. As a quick note, the original version of this work was presented in ARMA conference this year, and an extended abstract is available online in case you want it. So let's begin. So the presentation today will consist of 5 parts. First, I will describe the motivation and the motivation of our work. Second, I will introduce the induced seismicity risking process. Third, I will mention the data and the variables, and then I will describe the models and the analysis. And finally, I will end with the conclusions and the work in progress. So first of all, let's begin with some motivation of this work. For those of you who don't know it, the Permian produces over 10 millions of barrels of water per day from unconventional assets like Midland and Delaware. And as a quick reference, this means that per day, the Permian produces over 1,500 Olympic-sized swimming pools. Sorry, enough water to fill 1,500 Olympic-sized swimming pools, which is also equivalent to say that the Permian produces enough water that is enough to cover the demand of water daily consumption of more than 3 million of American households. As you can see, these gigantic volumes of water highlights the magnitude of the water management problem that the Permian faces. Among all the existing disposal methods to date, the only economically feasible one consists of underground injection. Therefore, the most common disposal method is via saltwater disposal wells, or commonly known as SWD wells, that inject fluid above and below the producing layer, as schematized in the figure here at the right. In this case, there is an injection well injecting below the producing layers. As we all know, this fluid injection increases the pore pressure, which changes the stresses in the formation, which can potentially induce pre-existing faults to fail and therefore become seismogenic. And as a reference of these processes happening in the Permian, we can cite the fact that over the last 5 years, the Permian experienced over 700 seismic events of magnitude 3 or larger. So in the figure here in the middle of the slide, it is shown the number of seismic events as a function of time. Horizontal axis shows years, and we can see how the number of seismic events have recently dramatically increased, as well as the magnitude of those events. Based on this, it is clear that it is of utmost importance to really understand the risk of induced seismicity before permitting or drilling any new saltwater disposal well. So now let's take a look at the current induced seismicity risking process. Over the last decade, the industry somehow developed induced seismicity risking to assess or evaluate potential location of these injections well before disposal. We all know that there are also industry-accepted modeling tools such as fault slip potential to assess the likelihood of induced seismicity. In addition, individual organizations leverage empirical data available, with each operator employing its own set of variables believed to most accurately predict the likelihood of induced seismicity. In Texas, however, it is the Texas Railroad Commission who regulates the oil and gas industry. Texas Railroad Commission is also known as Texas RRC or RRC simply. And in Texas, every time a new disposal well is proposed for injection, it has to be submitted to Texas RRC, who approves or disapproves these wells. So Texas Railroad Commission released these seismicity grading sheets shown in the slide here for the first time in 2019 and then revised them later. And it uses these seismicity grading sheets to assess all saltwater disposal wells applications submitted by different operators. And these seismicity grading sheets are summarized in the table here. In this grading system, Texas RC defined different variables. 5 of those variables are related to past seismic events. Two of these variables are related to faults. One variable is related to the confidence of the data. And one last variable is related to the cumulative injection rate within 4.54 kilometers from the well being considered. In this grading system, Texas RC assign grades that range from A to C minus by evaluating these variables and comparing those values with already defined thresholds for each variable. In this grading system, A corresponds to the lowest risk and C minus corresponds to the highest risk. In addition, Texas RRC differentiates between shallow and deep wells in this risk assessment. And they do so by defining different radial distance to which these variables are being computed. For instance, it defines a radial distance of 25 kilometers for deep wells, while it defines 9.08 kilometers for shallow wells. Surprisingly, to our knowledge, quantitative analysis of the predictive power of these risking variables defined by the Texas Railroad Commission is not available in the public domain. But given the high impact that these seismicity grading sheets have on the industry ability to dispose of these enormous volumes of water produced, we consider this an extremely important question, and this is exactly what we try to address in this work today. In order to do so, we construct from scratch data sets of 4,616 wells in Texas. And then we employ pure data-driven models to assess the predictive power of the model itself and also the predictive power of each individual variable exact as defined by Texas Railroad Commission. And the figure at the right, it is shown the Permian Basin. Deep wells are represented by the red triangle. Shallow wells are represented by this blue triangle. So now let's take a look at the data we use in this work. In order to perform our analysis, we use three different types of geospatial temporal data sources. First, of seismic events. In our study, we use all publicly available historical data from US Geological Service, and we consider only events of magnitude 2 and larger. Second, we use data of all mapped faults in the Permian Basin. In our work, we use the most current public data available for both shallow and deep faults. And third, we use data of all the wells in the Permian Basin. In particular, we obtain data of water disposal injection volumes as another relevant wells data from regulatory authorities via B3 Insight, which is a commercial vendor. And here in this figure, we can see the Permian Basin. This black line here delineates the boundary of the basin. This red line here delineates the border between Texas and New Mexico. Blue lines here represent deep faults, and all seismic events of magnitude 2 or larger are represented by these colored dots. Different colors corresponds to different seismic event magnitudes. And as a quick example of the recent seismic activity in the Permian Basin, we can note this point here. This corresponds to a seismic event of magnitude 5.4. It took place near Thanksgiving 2 years ago, and it's considered to be the third largest event in the entire Texas history. And most recent one, this point here, corresponds to a seismic event of magnitude 5.1 that took place a couple of weeks ago, September 9 this year. And this corresponds to be the second largest event in the entire Midland Basin. So in our analysis with this data, I should just show, we calculate the 8 variables exactly defined by RRC. Our analysis is constrained only to the Permian Basin area that lies within Texas state, as shown in this figure here. We know that the seismicity grading sheets can only be applied into Texas state, but also New Mexico authorities do not impose limits on the injection rates. They impose limits on pressure. Therefore, one of the variables defined by the RRC could not be computed in New Mexico. Therefore, we calculate the variables where they can be applied and also where they can be calculated. Then we proceed in a way that is schematized in this figure below. So for each well, we analyzed seismic events, faults, and total permitted injection rates within a buffer zone centered at that well of interest before the start of injection of that well. Then we build one single model of shallow and deep wells together, and we calculate each variable accordingly, which means shallow faults are used for the assessment of wells only, and deep faults are used for the assessment of deep wells only. And similarly, the total permitted cumulative injection rate of deep wells only account for adjacent deep wells, and in a similar way for shallow wells. Then we want to build a model that is able to predict whether a well will induce a seismic event or not. And this is the target of our model. Once we calculate the 8 RRC variables, we then proceed to label the data, which means we needed to assign to each instance of the data set one of the two possible outcomes, which implies to identify in the entire data sets which were the wells that are linked to an induced seismicity event. As we all know, given the complexity of induced seismicity, it's impossible to determine with certainty which well caused an induced seismicity event. Therefore, for labeling purpose, we had to adopt a certain criteria. And the final adopted criteria for a high-risk well was, first, there is one seismic event of magnitude 2.5 or larger within a radial distance of 4.54 kilometers from that well. And of course, the event occurs after that well starts to inject. And final, the two labels of our models are high-risk well and no high-risk well. And in this work, we use as equivalent terms, high-risk well or positive well or well linked to induced seismicity event. And here I'm showing you the 8 computed variables defined by Railroad Commission. Horizontal axis here shows longitude, vertical axis shows latitude. Each well is represented by a color dot. Different grades are shown in different colors. Grade A are shown in blue, and grade C- are shown in red. For instance, when looking at this variable called distance to the nearest fault, we observe here a significant number of wells in the southern part of Delaware in close proximity to faults by just looking at this grade map. In our work, we built 2 different types of models. The first one is a very simple analytical model, and the second one is a machine learning model. In this slide, I'm just presenting the simple analytical model, and the machine learning model will be explained in the following slides. So here, in this simple analytical model that we decide to call average grade model, we assign a grade for each well as the arithmetic average of all the 8 RRC variables. And then we classify that well by comparing that grade with a threshold value. If the grade is larger than this threshold value, the well is considered as a high-risk well. If the average grade is smaller than this threshold, the well is classified as a no high-risk well. We also range this threshold value from 0 to 3, being 0 the lowest risk or grade A, and 3 is the highest risk or corresponding to grade C-. So for each threshold, we then compare the model predictions with the label data, and we can compute 2 different metrics of the model classification performance. So we calculate the true positive rate and the false positive rate for this classification model. True positive rate is simply a metric that quantifies among all the actual positive wells or high-risk wells, how many of them were correctly predicted to be positive. And false positive rate is just a measurement of among all the actual negative cases or negative wells or no high-risk well, how many of them were incorrectly predicted to be positive. So for each threshold, we have these two metrics, and then we arrange the threshold within the range 0 to 3, and all the results are summarized in this curve here. Each point corresponds a classification value, a classification threshold, sorry, with its corresponding true positive and false positive rate. Of course, we then want to find what is the best threshold. And a good threshold would produce a good balance between true positive and false positive rate. Ideally, the best possible will produce a true positive rate of 1 and a false positive rate of 0. Therefore, in order to find the best threshold for our classification problem, we found the point in this curve closest to this theoretical upper left corner of the plot. And by doing so, we obtained that the threshold was 0.4. We then, for this threshold, compare the model prediction with the label data. And when studying the performance of these classification models, we can take a look at different metrics, depending on which property of the classification model we want to evaluate. In our problem, it is of critical importance to correctly identify the positive cases, which are the high-risk wells. Therefore, we paid greater importance to the recall. Recall is a measure that quantifies among all the actual positive or high-risk wells, how many of them were correctly identified by the model. This simple analytical model shows a recall of 76, which is considered large enough. It means it misses a relatively small number of high-risk wells. And also we found that the model presents an overall accuracy of 83.7. By overall accuracy, I mean the ratio of among all the predictions, how many of them were correctly, independently whether they are true positive or true negative cases. So we found that this very simple model is relatively overall accurate and high effective at identifying critical wells when using this optimal threshold. In addition, we built a random forest model to predict whether it will be high risk or no high risk well. For those of you who are not very familiar with the random forest model, the general structure is shown here. I'm not going to explain all the details, but it's an ensemble learning method that uses different trees built in parallel, and then it assigns the class of the well study as the class that received the most votes from all the trees. So in our work, we built a random forest classifier based on the 8 Railroad Commission variables that we already compute. Then we divide our data set into training and test set as 80-20% respectively. We maintain class distribution in this data split, which means we kept the same ratio of positive cases in the entire data set. The major challenge of our data is the highly imbalance between classes. Positive cases or high-risk wells account only for 2% of the total number of wells. Therefore, in order to overcome this challenge, we use random oversampling during the training, which is a method that artificially duplicates positive instance during the training to avoid a bias towards the negative wells prediction. We use scikit-learn library from Python. The hyperparameters were then optimized using the library hyperopt. We use 5 false cross-validations to find the best hyperparameters of the random forest model. And then for the optimized random forest model found, we compare the model predictions with the label data, and we then proceed to compute different metrics to assess the model performance of this random forest model. In this case, we obtain a recall of 76.2, which means that this random forest classifier means about 20% of the positive cases, which is considered acceptable. And finally, this model presents an overall accuracy of 81. So we conclude that this random forest model is quite effective at capturing the critical wells, and surprisingly, it shows a performance comparable to the average grain model that I just showed. In addition to building the predictive model, in this work, we were interested in understanding the predictive power of each of the Texas Verbal Commission variables to assess if each of the variables are indeed a good predictor or not. In order to do so, we explore variable importance with the goal of identifying the most predictive ones. We did so by using two methods. The first method is presented in the slide. It's called mean decreasing impurity from scikit-learn for tree-based models. And the results are shown here. The vertical axis shows the variables considered of the random forest model, and the horizontal axis shows the importance score of each of these variables. And it indicates the variable's contribution to the predictive ability of the model. This method shows that not all variables have the same predictive strength, and we can clearly identify that the ones that offer the most information gain are, in decreasing order, first, the distance to the nearest fault, second, the number of faults within the buffer, and third, the permitted cumulative injection rates. And in addition, we consider another method to study the variable importance, which is called variable permutation. This method measures the change in the model accuracy when randomly shuffling the values of each of the variables independently. The idea behind this is that if a variable is important in the prediction, then randomly shuffling the values will affect significantly the model performance. So in this plot, the vertical axis shows the mean accuracy decrease, the horizontal axis shows all the variables considered, and we observe that there are two variables that are identified as the most impactful ones, which are the number of faults within the buffer and the distance to the nearest fault. Then we also identify variables with a significant smaller impact, which are the maximum event magnitude and the permitted cumulative injection. And also we identify variables with negligible impact, which are the number of seismic events of magnitude 3 or larger, the number of events of magnitude 2 or larger, the distance to the nearest event, and the year since the last event. So we conclude that fault-related variables are identified as the most impactful in predicting high-risk well, and this was confirmed by these two methods shown here today. And finally, another study we performed was the risk prediction variability. So first, we studied by basin. We wanted to see how the model behaves across different basins. The figure here shows different basins. Red dots corresponds to Midland wells. Green dots corresponds to Delaware wells. And we proceed the same way. We train a random forest model and then identify the best model possible. And the performance assessment of these models for each of the basins are shown in the slide here. When looking at the Delaware model, we obtain a recall of 92.3, which means that the Delaware models only misses about 70% of the high-risk well in the prediction, which is considered extremely good. We also observe a moderate false negative rate of 27 and an overall accuracy of 74. However, when looking at the Midland model performance, we observe that in this case, the model struggles to predict high-risk wells. The model exhibits a recall of 37, which means that in this case, the model misses the vast majority of high-risk wells. We also observe a false negative rate of 62, which means that every time the model predicts a negative well, the vast majority is wrong. And the model presents an overall accuracy of 70. So therefore, we observed a significant variability of the model performance across basin. But when looking closer at the numbers of the Midland model, we observe here an extremely small number of high risk wells, in this case, just 8. And this explains the bad performance of the model, or could explain the bad performance of the models, since maybe the model was not trained enough to learn how to correctly predict the positive cases. And later, in this risk prediction variability, we consider different well depth classification. So in this part, we build separate models, one for shallow only and another one for deep wells only. Shallow and deep wells are schematized in this figure. Shallow, by shallow, we usually refers for wells injecting above the producing layers. And again, we proceed the same way, and the performance assessment matrix are shown in the slide. When looking here at the deep model, we observe a recall of 50%. When looking closer at the data, we observe only 2 high-risk wells in this test set, which means that in this case, the recall could be only 0, 50, or 100. Therefore, this deep model is built on an extremely small number of data points. Therefore, it lacks of statistical significance, and therefore, it leads us to unreliable results. Therefore, if you want to proceed this way, we need either more data points or change completely the modeling technique. And finally, to summarize very briefly, the main learning aspect throughout this work that I presented here today, I could mention first that this very simple analytical model, when using the optimal threshold and also the random forest model, both proved to be effectively at capturing high-risk wells. We also proved that Texas Railroad Commission variables indeed have predictive power, and this was the main question we had when we started this work. We observed that not all variables have the same predictive strength, and fault-related variables are the most predictive ones. And of course, these models have room for improvement. So currently, we are enhancing our models by adding new variables, such as first, real injection volumes instead of permitted injection rates as defined by IRC. We know that what the Earth feels is the realistically injected volume, so we are accounting for that instead of permitted theoretical rates. Second, we are accounting for the proximity to critically stressed faults. We know that not all faults will fail when there is an important fluid injection. Therefore, we perform a mechanical analysis of all the existing faults, accounting for the stresses in the field and the fault geometry to determine which of the faults are critically stressed and which segment of the fault. Then we are accounting for the vertical proximity of the injection to the crystalline basement. And finally, we want to account for the pore pressure changes produced by the injections, and we aim to build this variable using numerical simulations. And finally, the overall goal of this effort is to be able to improve ExxonMobil tool to assess the risk of induced seismicity for all these injection wells, with the goal to determine the optimal location of this injection well and also the optimal injection scenarios for safe operations in the Permian. And most recently, the industry is currently working with the Texas Railroad Commission on defining an improved set of risking variables, which we are currently assessing. And Stefan, probably you want to explain a bit more about the last point that I just mentioned?
Yeah. Can you hear me okay?
Yeah. Yes.
Oh, great. Yeah, so I'm just going to spend a couple of minutes here transitioning to Mariana's last few slides, because there has been work done on the data analytics front since her ERTech presentation in June. And Mariana, you alluded to it in the last bullet of your previous slide. So late last year, the Texas Railroad Commission did reach out to the industry to start a dialogue on how to improve the saltwater disposal permitting process. And at that time, there was also a new organization that was forming called the Texas Seismicity and Water Partnership. And so they took on the task of developing a set of recommendations to the Railroad Commission that included potential improvements to the seismicity grading matrix that Mariana just went through the analysis of. And for those of you who aren't familiar with what the Texas SWP is, the Seismicity and Water Partnership, it's actually a collection of operator representatives working injection and seismicity related topics. It's facilitated by staff from the industry trade associations like TEXOGA or the Permian Basin Petroleum Association, but you don't have to be a member of TEXOGA or PBPA to be a participant in the Texas SWP group. It's not owned by any one trade association. So if anybody's online who wants to join the Texas SWP and work with some of the operator representatives on making improvements to the disposal and the seismicity in Texas, just reach out to me and I can put you in contact with the right folks. So early last year, like I said, the Texas SWP began developing potential improvements to the grading matrix itself. And it became apparent that we also not only needed to propose improvements to the grading matrix, but also assess the behavior of any new variables that we're proposing, or any definition changes to existing variables in the grading matrix, or any changes to the cutoff thresholds that would denote the A, B, C minus risk levels. And so Mariana and I started working together to start assessing the proposed changes as well, not just the existing Railroad Commission risk variables, which is what the previous part of the presentation was about. And so that analysis is ongoing, but we thought we'd give you a little bit of an idea of how we're going about performing the analysis of these potential improvements to the risk matrix. It's a work in progress, so please keep that in mind, but we thought it'd be useful for the group to know. So Mariana, I'll throw it back to you to present that material.
Thank you, Stefan. And as Stefan just mentioned, here as an example, I'm showing just two potential variable who are candidates today. In this slide, it is shown the candidate variable total cumulative injection volume within 4.55 kilometers. And in the next slide, I'm just showing another one for your reference. So here in the plots at the left, it is shown the grade distribution on that variable in the Permian Basin. Again, as Stefan mentioned, the industry and Texas Railroad Commission define different range for different grades. In this case, for this variable, grade A corresponds to injected volume smaller than 10 millions of barrels of water. Grade D corresponds to an injection volume larger than hundreds of millions of barrels of water. And this is how the grade distribution looks in the entire area. And here at the right, we can see the histogram of that variable distribution. Different colors highlight just different grades for visualization. And by this analysis, we observe that grade A in this variable is the most prevalent grade, and it corresponds to 67% of the area of this basin. Then grade B accounts for 21%, grades, and then finally grade C and D are the least frequent grades, accounting for 7% and 4% respectively in the area. And as another example, a second improved variable is distance to the crystalline basement, not considered by the current seismicity grading sheets. In this case, we separate by well depth classification. In a similar way, the plots at the left show the grade distribution in the Permian area, and the figures at the right shows the histogram of that variable. For deep wells, we observe that 50% of the wells inject within 2 kilofeet from the crystalline basement in very close proximity. 18% of the wells inject at intermediate depth from 2 to 5 kilofeet from the basement. 25% of the deep wells inject between 5 and 10 kilofeet from the basement. And then only 7% of the deep wells inject at a distance greater than 10 kilofeet from the basement. When looking at the shallow wells, the distribution changes a bit. Only 2% of the shallow wells inject in close proximity to the crystalline basement as expected. 5% inject at intermediate depth between 2 and 5 kilofeet from the basement. Then the vast majority of the shallow wells inject between 5 to 10 kilofeet from the basement. And finally, 33% of the shallow wells inject at a larger distance than 10 kilofeet from the crystalline basement. We easily observe that deep wells are predominantly grade A, while shallow wells are predominantly grade B or A. And as Stefan mentioned, we are currently assessing other risking variables not shown today. And we are studying their distribution in the Permian area. And we are studying if the thresholds values defined by this group are too loose or too stringent, and if they need further refinement. And finally, the overall goal is to identify which of all the proposed variables indeed possess predictive power, and therefore can be used as reliable predictor of induced seismicity. And that's kind of what we wanted to show you today. Thank you very much.
Great, excellent. Thank you for the presentation, Mariana, and thanks for jumping on, Stefan. Great, great piece of work. Very nice overview and very, very nicely presented. So thank you for that. While people are putting their questions in the chat window, there is a bit of a conversation that took place. I think Stefan already addressed it, but Todd Shipman was asking, using the term risk, which is, I think, really using the Railroad Commission term, but I think Todd was pointing out that it's more likelihood or hazard parameter that's being predicted as opposed to any consequences of the event occurring.
Yeah, that's right. And when Mariana showed the labeling process, that's one of the trickier parts of doing this analysis, right? Because what you're trying to do is assess the predictive power of the risking matrix process, calibrated against which wells actually are associated with seismicity or not, right? And how do you define which wells are actually associated with seismicity? Because that's a really difficult thing to do. And you have to kind of put a rubric in place to kind of develop that label. Otherwise, you don't have a training data set, right? And those labels are purely, and yeah, Mariana's showing it right here. Those labels are purely labels that speak to the likelihood of triggering seismicity or seismicity above a certain magnitude near your well. We're not addressing any kind of infrastructural fragility type of consequence aspects.
Great. So I see a few questions coming into the chat window, but before we get to that, I was going to actually ask a question myself based on this slide. So I'm wondering if you've given any thought to what's being labeled as a high-risk well based on that buffer in particular, the assumption of a 4.54 kilometer distance. If that was larger, would there be more wells identified? And I guess is that the best value to be using? I don't know if you've done any tests on that.
Mariana, we've talked about that. I'll let you take that if you want.
Yeah. Definitely it will change. The larger the radius, the higher the high risk well numbers we identify, therefore the better the data set. But it's not so simple. There is a point because the infinite radius will consider all high risk, all wells high risk grades. So there is something in between. So it's it is partially true, but it's not like it's not as simple as that. Because the extreme case will be considered infinite radius, therefore all risks are high risk wells. So there's something So it raises it's a different problem. But yeah, definitely this is a central variable of our model.
Yeah. Yeah, to me, it's a balance, right? If you increase the radiance at if you increase the radius, your positive labeled wells that are, let's say, associated with the seismicity does definitely increase, and you have less imbalance. But you also run the risk of labeling wells as being associated with seismicity that may not be, right? And so your training data set accuracy may start to degrade potentially.
Yeah.
Yeah, appreciate that. And I did have one other question. There's questions coming into chat, so at risk of taking taking kind of executive privilege here with the questions, but I guess I'm wondering a little bit about just the timing of the fact that we're looking at seismicity prior to injection as the flag, and I'm struck by the fact that seismicity variables are so low in terms of importance in predictive power, and I wonder if part of that could just be that these are older wells that are problematic, and the seismicity hasn't been had enough time to express itself for some of those older wells. And I'm curious, Mariana, have you looked at any sort of temporal changes? Is the predictive power, for instance, better for more recently drilled wells as opposed to maybe some more historic wells?
In this analysis, we that's a good question. We consider all wells from the early, I think 80, the first data point we have until January 2021. So they have time to kind of like produce enough pressure change to induce seismicity. But we consider all of the wells until 2021. We didn't consider the most recent one, so like the pressure changes produced by them are not accounted here. So that's why we define that threshold time. Stefan, I don't know, you want to add something
No,
more?
it would be interesting, Mariana, for us to kind of take a look at maybe even just as simple as breaking the data set into two pieces, right? An early data set and a later data set, because I would expect the predictive power of the seismicity variables to be better in the later data set because there's more historical seismicity with which then to guide the prediction, right? Those early SWD wells, if you're trying to assess the predictive power of historical seismicity, well, there wasn't any historical seismicity, or there was very little historical seismicity at the time. And so those might be artificially degrading kind of the assessed predictive power of the seismicity variables. And to Sean, your question as well, the seismicity variables were not assessed to be unpredictive, right? All the variables had some level of predictive power. It's just that it looked like in this particular assessment, faults tended to have a higher predictive power than the seismicity ones. And there's also reasons why the faults may be artificially inflated as well, because we don't know what the fault interpretations actually were 15 years ago, when a certain SWD well was being permitted. We can't take a time machine and kind of know when that was. But we do know what our understanding of the seismicity was at the time because we have the historical seismicity catalog. So we ended up being forced to use the present day fault interpretation, right, as the variable for the fault variables that we were assessing. And so as a result, there might be a little bit of an artificial inflation of the predictive power that we assessed for the faults.
Right. I'm pretty sure the expression hindsight's 2020 probably comes from exactly that point. Right? But anyways, just to move on to some of the questions in the chat, Adam Beggs asking a question on if you could tell wells closer to basement rooted faults, if they're more prone to larger events than just proximity to more shallow faults. And I guess raising the point of just this subset, the fault mapping kind of information.
Yeah, I mean, if the question is partly asking, is there some predictive power to predicting the magnitudes? Of course, the answer is that we didn't assess that, right? We assessed the likelihood of a magnitude to a greater event within 4.54 kilometers. So anything above that threshold was considered, a high risk well. So we didn't assess any predictive power of magnitudes. But maybe that's not the question, Sean or Adam.
Yeah, well, maybe we can move on and come back to that if we have more informal conversation at the end, because there's maybe a few questions here. So moving on, Luke Frash is asking, I think it's more on the mitigation side. So if something's flagged as a risk in the Railroad Commission grading, what the impact is in terms of the permit. So is flow rate, pressure, or depth limited in reaction to that?
Right, right. Yeah, and I think Mariana, you touched on that when you said, we weren't including New Mexico wells, right?
Yeah.
The permit limits that are imposed on wells as a result of this risking process at the Railroad Commission is applied to the ceiling or the maximum injection rate or volume, right? So, wells that have a grade A or a low risk grade are allowed to inject, and I can't think of offhand, I think it's 30,000 barrels a day or more. Wells that have a very low grade, a C minus, could be given a very low volume, like 10,000 barrels a day, or maybe have their permit denied altogether. New Mexico doesn't permit based on volumes or injection rates. They permit more based on pressures. And so for that reason, that was one of the reasons why we decided to keep New Mexico out of the assessment.
Great. Then Aaron, moving on, Aaron Budebog with Nanometrics has more of a machine learning data analytics kind of based question, I think. He's wondering if kind of feature importance can be really properly assessed, I guess, when the overall model performance isn't good. So maybe looking at some of the cases you pointed out with small populations and striking on the Midland side, for instance, how the performance was not as good as on the Delaware side. So
Yeah.
any comments?
Yeah, sure. The model is as good as the data we have. So if the model lacks of the class of interest we want to predict, then even though like we use different models, the model won't be good enough. So as I said, in this problem, the main challenge is that the high-risk wells are only 2% of the entire data set. So we are using an artificial method to kind of reach a balance of classes. But of course, if the better the data, the better the model. That's for sure. So in order to improve our model, it would be better if we could have more wells that induce seismicity to actually build a better model. Yeah. Like as an example, the deep model has only 2 wells, so that's kind of completely lacks of statistical representation. Yeah.
Is it fair to say, Mariana, that our confidence in the assessment of the performance of the entire model, the results of that we probably have higher confidence in than the results of assessing the individual variables within the model? Is that fair to say?
Sorry, what do you say? Sorry,
I guess it feels to me like when you're assessing the model overall and you're coming up with, let's say, a recall value, our confidence in those results is probably pretty good. The confidence in the results of analyzing the individual variables, right, might not be as high because of the issues with the model, being biased in some ways too.
Yeah. I mean, the variable analysis actually study how each variable impacts the model prediction. And the first method shown, it actually the first method studies how much each variable contribute to reduce the impurity in the classification. That's one analysis. But also, for instance, as I mentioned, we have different metrics. We pay attention to only the recall, but there are other metrics that also tell us a lot of information. For instance, some of the models I show are really bad at predicting high-risk wells, but they are perfect, almost perfect at predicting not high-risk wells. So the recall is not the only thing we should take a look, but also like they are kind of independent analysis. Because once we have the model, then you do a sensitivity study about to determine which are the most impactful ones, but the model is already built.
Mm-hmm.
So yeah, of course, if the model is bad, then you will obtain an analysis from a relatively bad model. That's all what you can get.
So maybe just moving on with some other questions. There's some good questions in the chat. We probably don't have time during the formal part to get to everything, but we'll kind of continue to work through. And then again, Mariana, if you're and Stefan, if you're available afterwards, maybe we could have more of a informal Q&A. But the next question, Fernand Sabaderi is asking if you looked at the timing of injection, the timing of seismic events, and if I guess, to maybe speculate on the question a bit, is there a parameter tied to the timing that might be an important predictor?
Like how long after the well started did the seismic event occur, for example, I'm guessing.
Yeah, or maybe total volume into a well as a predictor.
Yeah, we are not accounting for the time in this analysis. We are compressing the time, let's say, in a very simple way. For instance, when counting the seismic events after the start of injection of one particular well, we don't consider any time window. As long as it happens afterwards, we link that seismic event to that well. And we know that also that's a big assumption.
Yeah. Yeah, I mean, pure logic, I mean, you don't want to ding a well for a seismic event that happened before it came online. I guess the only other timing piece that we've built into it, Mariana, is that we decided not to use wells that have come online very recently, right?
Yes.
Because wells that have come online very recently, they may be a high risk well in reality, but the seismic event hasn't quite occurred yet, right? And so we don't want to artificially inflate the negative predictions that way.
Yeah, all the wells considering these data sets are wells that started to inject before January 2021. So
Excellent. So maybe we'll just hit one more formal question and wrap this up with a question on faulting from Jens. He's just asking if you've got comments on how the fault mapping should be done, maybe scale or completeness of the fault mapping. And I mean, just a little bit of quick comment on this from my side. I think we're fortunate that we have this is a research group doing such a fantastic job at a public fault network to start with. These maps are never perfect, but I think we're much further ahead in Texas than maybe we are elsewhere with just kind of public information. But I guess also that question, just awareness of the potential hazards near an injection site based on these faults.
Sure. Yeah, I can make a good comment. While doing this work, we obtain most updated faults data from the public domain. So we updated our model. And here are the authors of the published data. And we observed that these updated or corrected mapped faults improve the model performance. Also, I don't know what. And also one comment. In our work, we are using all these faults, and we are aware that the author who published these faults also provide an interval of confidence of each fault. But in this study, we are considering all these faults to be correct. And also, I understand Stefan can explain this more better than me, but Exxon has proprietary fault data, but in this study, we consider only public data because we are replicating Texas RRC evaluation.
Yeah, we made sure that we only use public domain information, Mariana. To follow on what you said, though, these aren't ExxonMobil's risking variables, right? We have our own risking variables that we use that share similarity with the Railroad Commission's. One of the things that we looked into with regard to faults is not all faults are created equal, right? Not all faults are prone to the same stability, and so we are analyzing the fault variable by only using faults that are within a certain number of degrees within kind of the low stability azimuths in relation to SH max. And those, when you only include faults that have a high tendency to fail based on the regional stress regime, the expectation is that your variable using the faults would be even more predictive, because you're getting rid of the faults that are very unlikely to slip in the first place, and not using those to encumber the well that you're risking.
Great, excellent. Well, there's more questions in the chat, and again, we can, if the people asking the questions, if we haven't got to it, if you want to stick around, we can maybe continue the conversation. But we've reached the end of the hour, so the formal part of the webinar, so we can maybe kind of wrap it up. And so first of all, on behalf of ARMA and the Induced Seismicity Committee, we thank you, Mariana and Stefan, for sharing this piece of work. It's really an excellent piece of work and an excellent presentation. So again, we thank you for your participation, and thank you everyone for calling in. As we mentioned at the start, we do have a change in schedule for our November speaker, so we're still working to pin that down, but we'll watch for Madi's email, and we're hoping to have another exciting webinar to follow for the November talk. Thank you, everyone. Have a good day, and again, thank you, Mariana, Stefan, and Exxon. These series of talks that Exxon's done for the webinars have been really interesting. And as I pointed out in the introduction, some of the most popular downloads for the recordings. So thank you.
Thanks. Thank you for being here. Bye.